Thank you for the kind introduction. Hi, guys. So I hope you had good coffee and you guys are awake. Try to ask questions. That makes things more interesting. So here, I'm from the Ohio State University. I work with Dr. D.K. Panda. Unfortunately, Dr. Panda couldn't be here because of a conflicting travel. Please feel free to interrupt me at any point in time if you have any questions. So this is kind of a, let's say, moot point right now because Dr. Milbagger already showed you this slide. So yes, the high-end computing systems have been like rapidly increasing in capacity over the last several years. And yes, this slide is maybe a little wrong right now, as Dr. Magro pointed out. We are expected to have an Exaflop system around 2020 to 2022 from different countries. So with this kind of a speed up in HPC, where does that leave us in terms of the other pillars of what is building up our ecosystem, big data and deep learning? Now, what we are seeing is a kind of convergence happening. The problems that all three domains are facing, HPC, big data, and deep learning, are kind of similar. So can we apply experiences and knowledge that we gained from one domain to another domain? And how can the domains learn from each other and solve problems which are common to all of them? So that's what the talk is going to be about. And I'll mainly focus on two aspects of it. The traditional HPC, which has the programming models like message passing interface, programmable or partitioned global address space, and the use of accelerators like the GPUs from NVIDIA. And the second is deep learning. So 5 years back, it was big data this, big data that. Now it's deep learning this, deep learning that. So how can you have a talk without something about deep learning in it? So what this talk is going to say is, what is this deep learning and what challenges does deep learning bring to the current programming models like MPI? And how we at the Ohio State University are trying to address some of these challenges. So this slide gives you a quick overview of the parallel programming models. I'm sure most of you are familiar with it. So you have your traditional shared memory model. You have your distributed memory model and the partition global address space models. And out of these, MPI is, let's say, the dominant programming model for HPC at this point in time. But why really think of the others, like your partition global address space or PGAS models like UPC, CoArray Fortran, or OpenSHMEM? So the basic reason is this. Different programming models are good at different things. So let's say while MPI is really good at static communication patterns, it is not so good to express dynamic communication patterns. Now, MPI3 RMA is a step in that direction. So can we take the best of both worlds? Can you have an application and say that, OK, the application has so many parts. Can you write some of those parts using MPI and some of the other parts using a different programming model which is best suited to it, so that you express or you use the right programming model for the right portion of the program and get the best of both worlds, the best of your distributed computing model and the best of your shared memory computing model to get the best kind of performance? So that brings us to the following slide. How do you bridge using the programming models, the advances in hardware architecture that's happening? So we have a lot of multi and many core accelerators and processors like Intel Knights Landing. You have networking technologies coming up from Mellanox and Intel like InfiniBand and Omni-Path. You also have storage solutions. So this is basically what the supply side is. But the demand is being driven by end applications from various domains. So earthquake prediction, oil and natural gas, so on and so forth. So how can modern programming models and associated middleware bridge the gap between the supply side at the bottom and the demand side at the top? That's basically what we are trying to solve here using various advanced communication methods. Now, there is also a wide array of co-design opportunities available. So if you are smart enough, you can try to redesign your application and your middleware with the view of what is happening on the other side to get even better performance. Now, an example of this I'll try to show later on in the deep learning section of the talk. So this is the standard slide we give everywhere. So being from the MVAPICH group, I have to show this here. We are pretty good, and we are being used by a lot of people out there. For more information, please visit our website. And we've been in the community for a very, very long time. And this is a list of all the releases that we have made over the last 16 years or so. This is a broad architecture of the MVAPICH family. So we have support for good point-to-point communication using various transport mechanism like across nodes as well as within a node. We'll try to show you some of the more newer and more exciting things that's happening on our front, and how we hope that is going to tackle some of the challenges for the emerging exascale era. So the one thing you would need, obviously, is good scalability. Now, what does this entail? So good scalability entails support for highly efficient intranode and internode communication, job startup, optimized collective communication. Now, Dr. Magro mentioned that deep learning applications use a lot of collectives. So like all reduction, or all reduce is one of the most common collectives used for deep learning. So that is really required. And how do you take advantage of some of the newer features, architectural features, to accelerate these collectives? So like, let's say, can you use CMA or XPMEM to accelerate these collective operations within a node as well as across multiple nodes? And how do you measure and analyze the impact all of these high-performance libraries and applications have on the network? So can you have an integrated fabric analysis and monitoring suite to see what is actually going on in the network, and how you can correlate that with what's happening in the application? So like we get pretty good performance with all different kinds of like processor architectures as well as interconnect architectures. This slide just shows you a performance comparison for various generations of like hardware, from TrueScale QDR all the way to Omni-Path and ConnectX-5 EDR. So this is from like 40 gigabits per second all the way to 100 gigabits per second. So similarly, we have like excellent bandwidth. So we are able to saturate the network for unidirectional as well as bidirectional bandwidth here. Now, all this is good, but the first and foremost that any parallel programming middleware would need is to actually start up a job. So you could have a Ferrari or a Lamborghini, but if the car takes about 15 minutes to start up, then nobody is going to use it. So just like that, with any MPI library or any middleware, what you would need is a good startup mechanism. Okay. Now, if your application runs for maybe like a couple of days or so, then 15 minutes, I don't care. But if you're trying to do debugging, or if you're doing maybe more of a short-running application, then job startup becomes extremely important. So that is where we are trying to focus and ensure that we get excellent job startup performance at very, very large core count. So here we are trying to show the MPI init time and basically a small hello world time on KNL plus Omni-Path systems at the TAC Stampede and the Oak Forest PACS in Japan. So as you can see, we get excellent startup performance on these systems at almost full system scale. So this is the first step. So when a developer or an application user starts off his parallel program, you want it to start up like that. It shouldn't take forever to start up. So this is the first and foremost. Now, once you have done that, so you need some improvements in the basic point-to-point and collective operations. So what are we doing in that regard? All reduction is a very, very common collective operation in a lot of HPC and deep learning applications. The only difference between the two is that HPC relies on maybe 4-byte and 8-byte all reduce, but deep learning would rely on maybe 30 megabyte or 60 megabyte all reduces. So it's just a difference in the scale. So here we are focusing more on the HPC side. And once you go to the next section of the talk, we'll show what we are doing on the deep learning side. Now, Sharp is a technology from Mellanox, which tries to do in-network reductions. So previously, what would end up happening for reduction operations is process A would send a message to process B. Process B would get that, try to do whatever reduction operation it is, like a sum or min, max, whatever it is, and send the result back. And finally, the results will be propagated to everyone. Now, this has a lot of additional message transfers. Now, can this be made better if the switch itself does the reduction? So all the processes send the data up to the switch does the reduction and sends the data back. So such kind of hardware-assisted collectives have a significant potential for improved scalability at scale. So that's what we are trying to show here. And for almost all HPC applications, there is some sort of knowledge reduce that happens to find out if the application has converged or if some sort of a terminating condition has been reached. So these sort of improvements has the potential to affect a wide variety of HPC applications out there. And here we are trying to show the same benefits with a couple of applications, popular HPC like mini benchmarks like HPCG and mini AMR, which is part of the Mantivo suite. So this is again showing the performance of MPI already with these designs on the TAG Stampede 2 cluster at a very large core count. So as you can see, you get significantly improved performance for the medium to large message range for all reduce with whatever new designs that we have in MVAPICH2. Now this was for internode. How about a single node? So if you guys saw the NSF exceed usage chart, you would see that about 80 to 90% of the use cases on these supercomputing systems are small 1, 2, 4, 8 nodes. It's not your typical like 100, 200, thousands of nodes. So intra-node performance is very, very important. Now, typically, if you look at it, there are different kinds of methods people use for intra-node communication. So you have a shared memory-based mechanism, or you have your kernel-based transfers, or like multiple others. Now, all of these collective operations have traditionally been staged over point-to-point operations, which means that, as Dr. Magro's talk mentioned, it goes over all the overhead of the MPI library, tag matching, send, receive, and all that jazz. So can we avoid all of these and have direct mechanisms using kernel-assisted techniques like Linux's cross-memory attach to see if we get better performance? So that's what we are trying to show here, to see if we can use Linux's CMA method to get better scalability on the emerging many core systems. So here we are showing the example of MPI gather on the Knights Landing nodes with 64 processes per node. And we get similar performance on the other many core architectures like Broadwell as well as OpenPower. So as you can see, we get significantly improved performance at various message ranges compared to the other MPI libraries which don't have such optimized collective mechanisms. Now this is one way you can do it, but this still has the overhead of having to copy the data from the remote process to the local process. Now XPMEM is something which kind of changes the game completely. XPMEM allows you to do direct load store operations on a remote process memory. And it does not incur the overhead of the locking that CMA kind of kernel-based techniques have. Now with XPMEM-based designs, we can fundamentally rethink the collective algorithms and see if processes can operate directly on a remote process application buffer. So this is not an internal MPI library buffer, directly on a remote process application buffer to perform load store operations. So this is fundamentally changing the way in which the collective operations inside MPI has been thought of till now. And with these kind of advanced schemes, we get significant benefit for reduce and all reduce. Now, as you guys know, these large message reductions are kind of the heart of your deep learning applications. So if you take a look at Microsoft Cognitive Toolkit or CNTK, which is host-based, and it also has a GPU variant, these sort of designs have a significant potential to improve the performance of these kind of applications at scale. Now, we do all of these things, but as I mentioned, how do you evaluate the impact these have on the network? So that's why we try to design what is called the OSU InfiniBand Network Analysis and Monitoring Tool. So what INAM does is to work with the job scheduler, for instance like Slurm, and the MPI library to tell you what's going on end to end. So given a link, can you figure out which job is contributing to the traffic on that link, or which process in that job is contributing to the most traffic on that link? So that's what we are trying to show here. Now, any other network profiling tool will not give you this information, basically because it is not interacting with the middleware. What it can tell you is, hey, you have this much traffic going on this particular link, and this is where it came from. But it cannot tell you which was contributing to it. So that is one major differentiating factor between what we are trying to do here, so and whatever is available in the community. And one thing that we would like to do going forward is to see if the same can be applied to other middleware like big data or even deep learning stuff. So on this slide, we try to show how INAM displays the per process or per job view of what is going on in a particular link. Now with that, let me head over to some of the designs we have for the unified runtime, the MPI plus PGAS stuff. So as I mentioned, MPI is good for some sort of communication operations, whereas your partition global address space is good for other. So what we are trying to show here is, can you combine the best of both worlds? Can you take some real applications and see if they can be redesigned so that portions of them use MPI and other portions of them use other programming models like OpenSHMEM or UPC, and see what sort of benefits they gain. So here we are showing the example of Graph 500 and SORT, and we are trying to see how the use of MPI and OpenSHMEM at appropriate locations can give you the benefits that neither one model can give you. So as you can see, there's significant, significant benefits that can be obtained over your pure MPI or your pure OpenSHMEM models for real applications at very large scales. So this is again showing the examples of how optimized OpenSHMEM with Intel's AVX and MCD RAM can give you benefits on the latest Knights Landing platforms over the existing many-core or let's say multi-core Broadwell kind of architectures. So with that, let me head over to the GPU portion of the talk. Now, how many of you are familiar with the concept of CUDA-aware MPI? Anybody? Some. Okay, a few. Now, typically, if you think of a GPU-enabled application, how would you go about doing communication for that application? The typical process would be the application developer would write a CUDA, would launch a kernel. After the kernel finishes, they would do a CUDA-mem copy of the data from the GPU to the host, do a MPI send or whatever your favorite programming model is, send to a remote host, and then copy it back and continue your application from there. Now this is low productivity for the application developer because now they have to do a lot of extra CUDA-mem copies. And it is also poor performance because they are probably only doing CUDA-mem copy, which is not the most optimal way. Now why is that so? Can anyone hazard a guess as to how many different communication paths are there for, let's say, GPU to GPU or GPU to host communication? Just a guess. Okay. So there are about 11 different communication paths available, depending on if you are doing GPU to local GPU on the same socket, on a different node, depending on the relative locations of the GPU and the IBHCA. So for an application developer who's a climatologist or let's say an oil and gas expert or something like that, to figure out all these 11 paths is virtually impossible, and it's asking something unreasonable of the scientists there. So what we are trying to do here is trying to see if we can abstract all of these things from the application developer so that all they have to do is an MPI send and an MPI receive, and the library takes care of all the complexities of data movement internally. So this is what we refer to as a CUDA-aware MPI. Now this will give you high productivity because you don't have the overhead of the CUDA-mem copies, and high performance because the MPI library is now figuring out all those 11 paths and trying to use the best path for the best sort of communication operations. Now, with this kind of designs, this is the kind of performance benefit that we can give you for internode GPU to GPU data transfer. No other MPI library in the world can claim this kind of performance numbers. So you get 1.88 microseconds, which is very close to the kind of performance your host-to-host communication gives you. Now, host-to-host communication right now is around 1 microsecond or slightly less than that. So this is device-to-device internode with MVAPICH2 GDR using the latest ConnectX-4 EDR and the Volta GPUs from NVIDIA. And similarly, you get very good bandwidth as well for like small, medium, and large messages, as opposed to the designs that don't have advanced capabilities. Now, the benefits don't just stop at the microbenchmark level. they also permeate to the end applications, because you can show a lot of benefits at the micro benchmark level for a lot of cases, but if they don't permeate to the end application, then it's really useless. Who cares? Who cares if latency or bandwidth or bidirectional bandwidth gives you very good performance? If your end application is not able to use that to deliver reduced application time, then nobody cares about your designs. So these are the kind of benefits the advanced designs have on, for instance, like HUMD Blue, which is a molecular dynamics application at different number of GPUs. Now, this is something else that we are really proud of. So this is an ongoing collaboration with the Swiss National Supercomputing Center and Meteor Swiss, which does the weather prediction for all of Switzerland. We are working with them to see if we can accelerate their weather modeling schemes using our advanced designs. So it's likely that next time you travel to Switzerland, either on work on vacation, pick up your iPhone and open the app to see what the weather is. MVAPICH2 is powering that solution behind the scenes. So these are some examples of real-life impact of what we are doing in our group. Now, of late, with OpenPower and ARM coming up, we have been trying to see if we can have optimized designs for those kind of systems. And we are showing some preliminary numbers here showing how MVAPICH2 compares to other MPI libraries for intranode performance on OpenPower as well as internode. So as you can see, we are better or equal to the other MPI libraries like Spectrum MPI and OpenMPI on the OpenPower system. So similarly, this is the performance of device-to-device transfers on the current OpenPower or Power 8 systems. So as you might see, we don't get that 1.88 microsecond number here, but that's basically because of a system limitation. Some of the advanced technologies currently don't work on the Power 8 systems because of hardware issues, but they are expected to work on the Power 9 systems based on the feedback we got from NVIDIA and IBM. So once they are out, once Sierra or Summit, the actual systems are out, we hope to get the same kind of performance for your communication performance on the Power 8 or on the Power 9 systems. So again, these are some host-based collective numbers. So earlier I had presented like collective performance numbers with CMA and XPMEM on x86 systems. So these are the same kind of performance numbers on the Power systems. So as you can see, the benefits are really available across all different kinds of architectures. This is again the performance that you get with XPMEM-based collectives. So you get significant benefits in the performance of your very large message collective operations, which is critical for your deep learning kind of workloads. And these are some very preliminary numbers on the ARM V8 system. So you get pretty good intranode communication performance on the ARM systems. Now, as I said, all of these are well and good, but if they don't really translate to the performance of end applications, then it really doesn't matter. So what we are trying to show here is the impact these have on the performance of end applications. So here we took the SPEC MPI benchmarks and ran it on the KNL plus Omni-Path systems, and we are trying to compare different MPI libraries here. So as you can see, MVAPICH performs pretty well compared to Intel MPI on the KNL as well as the Skylake system. So both of these systems are on at a TAC. They are part of the Stampede 2 cluster there. And this is the kind of application scalability we get on the Skylake as well as the KNL nodes. And this is kind of a community effort. It's not just us doing this. So we have different organizations like SDAC, TAC, which are part of this, and they kind of send us these results, and we host them on our website. So if you have any similar details, please do send it to us. We can post it on our website with the appropriate acknowledgement to you. So with that, let me head into deep learning and try to highlight what some of the challenges for MPI runtimes are in the new era of deep learning frameworks. Now, deep learning has kind of changed the game altogether, because typically HPC relied on, let's say, a few kilobytes or up to a couple of megabytes of messages. In the deep learning field, your communication volume is staggering. You have several megabytes of data to transfer from device to device or host to host. So it fundamentally changed the way in which middleware developers were thinking of their communication protocols. So that was one big thing. And most of the communication till now have been based on GPU buffers. Now, there is a common notion that GPUs are great for deep learning and CPUs are not. That is actually not true. The performance you get from deep learning is fundamentally dependent on your math operations. Now, NVIDIA over the last few years have optimized the hell out of the CUDNN library. So that is the fundamental, that plus the good hardware is a fundamental reason why you are getting excellent performance with NVIDIA hardware for deep learning applications. Now, Intel recently have updated Intel MKL to have similar math operations. Now, if you use KNL plus Intel MKL, you get pretty good performance with deep learning applications like CNTK as well. So whenever you see marketing slides either from Intel or from NVIDIA, what you need to think of is, are they using the right hardware? And more importantly, are they using the right software for the hardware? So if you are not using the right math library, your performance will really, really suck. So that's one thing you need to keep in mind. And there have been a lot of existing efforts, both from the Intel side and the NVIDIA side, to have better scale-up performance and scale-out performance. Now, what is scale-up? It is single node performance. So if you have 8 GPUs on a node, how do you use all those 8 GPUs to get the best possible performance? So that's basically scale-up. Now, scale-out. So so far, most deep learning practitioners have been limited to a node. They have not had the need to go beyond a node. Now, scale out is where HPC really comes in. How can you take that thing that runs on one node and maybe takes 1 hour to finish? Can you take that to 10 nodes or even 100 nodes and make it finish in 1/10 or 1/100th of a time? So that's where scale out comes in, and that's where the feedback loop happens. So HPC has been doing this really, really well for the past 20 years. Scale out is what HPC lives on. But for the deep learning folks, that's completely new. So can we bring good scale up as well as good scale out performance for your emerging deep learning applications? And as I mentioned earlier, are there any co-design opportunities? Can you look at the cross layers? So if you remember Dr. Magro's talk, he mentioned that there are different layers in your deep learning application, right? So what are the dependencies between layers? Can you identify them and propose newer co-design opportunities between the deep learning application and the middleware to get better performance? So that is where we are trying to head towards, to have better scale-up performance and better scale-out performance through co-design of deep learning applications and your middleware. And these are some performance numbers that we have done with MVAPICH2 GDR and comparing that to Baidu All-Reduce. Now, as you can see, you get significantly improved performance compared to the Baidu All-Reduce and OpenMPI with MVAPICH2. So this is one thing that you would notice differently. So earlier we were looking at the very small message range, but now we are looking at the extremely large message range. So this is like 8 megabytes onwards up to like 512 megabytes. So that is where your deep learning workloads are currently. Yes? Sure. Yeah. Almost done. Thank you. And this is the performance comparison of MVAPICH2 GDR versus Nickel 2. How many of you are familiar with Nickel 2 or Nickel? Okay, so Nickel is basically a GPU to GPU communication library from NVIDIA, and it is specifically geared towards deep learning. So it does very good broadcast, reduce, and all-reduce, which is basically what deep learning needs. So MVAPICH2 GDR is able to outperform the Nickel 2 library from NVIDIA on both 1 GPU per node and with multiple GPUs per node for operations like broadcast as well as reduce and all reduce. So basically what we are trying to highlight here is that MPI is pretty good. Now if you look at a lot of let's say companies like Facebook who came up with Glue or NVIDIA who came up with Nickel, the basic motivation there was that, okay, MPI is too complicated for me. I don't want all of that. Let me try to do something smaller and see if I can get away with it. So what we are trying to say is, hey, we have been doing this for about 20 years now. We know how to do a broadcast. We know how to do a reduce. We know how to do an all reduce. Why do you want to reinvent the wheel? Why don't you try to optimize your existing MPI library for your end use cases. Now, this is what Intel MLSL does. Now, Intel MLSL tries to expose like a new API for deep learning practitioners, but underneath it is using Intel MPI to the best of my knowledge. So that is what we are trying to ask here. Why do you want to reinvent the wheel when things are already there? Why don't you just reuse them and get the kind of scale up as well as scale out performance that you can get? And this is the kind of benefits that you can get with different workloads if you use the right set of solutions at the application level, I mean the deep learning, let's say framework level, and the MPI level. Now, let me wind up with one last thing. Currently, like deep learning requires a lot of memory, more memory than the current systems are able to offer. So this brings us to the problem of out of core. What if your deep learning problem does not fit in the available memory? So how do you do out of core deep learning training? So you can either stage it, or you can use the concept of unified memory that NVIDIA provides to have efficient designs for out of core training of neural networks on NVIDIA GPUs. So that's what we are trying to show here. So on the left-hand side of the graph, we show the trainable or in-memory region. And on the right-hand side, it is the out-of-core or non-trainable region which is currently there. We are trying to propose designs where we can have optimized designs for out-of-core training, and it performs significantly better than existing solutions for out-of-core training. And with that, let me wrap up. These are some of the plans that we have for Exascale systems. And we have other presentations. So Dr. Jiahui Lu will be presenting on DLO-BD next. And we have other presentations from the group tomorrow as well as day after. These are funding acknowledgements, and more importantly, these are some personal acknowledgements that we always like to make. I am here as well as like Jiahui is here because of the work done by guys who came before us in the lab. So some of them are actually here, Matt and Raghu. So we are actually standing on the shoulder of giants when we present this work here. And we'd like to acknowledge the effort that all the previous students and staff members made to make this presentation possible. Thank you. And with that, if there are any questions, I'm more than happy to take them. Okay. Okay, I'm done, guys. See ya.